The matrix inverse. This is one of my favorite topics in linear algebra because of the nice abstraction you get from it. So let's get started. So first off, what is an inverse? To answer this question, we've somewhat talked about this earlier on in the course. It really depends on your operation. So if I'm looking at the integers and my operation is addition, then the inverse of 2 is negative 2. And the inverse of 1 is negative 1. And the inverse of negative 7 would be a positive 7. Because 2 plus negative 2 is 0, 1 plus negative 1 is 0, and negative 7 plus 7 is 0. So nothing too shocking. Now if I looked at the integers again, but with multiplication, I could ask, what's the inverse of 1? Well, that is the number that I multiply by 1 to get 1. And so it's itself. And if I looked at negative 1, well, inverse of negative 1 is again itself, negative 1. But 2, well, the inverse of 2 would be the number x, such that 2 times x is 1. Now this number here, this x, where must it come from? Well, it must come from the integers. So is there an integer that when I multiply it by 2, I get 1? Well, no. That does not exist in the integers. And so you see, this notion of an inverse is deeply tied not only to the operation, but to the set in which you're working. So that's a very interesting thing, because when we move on to matrices, you're going to ask yourself, if I have a matrix, does the inverse even exist? Okay? So let's hear. The inverse of a matrix, so we're defining this, is some matrix B such that when I take A, I multiply on the right by B and on the left by B, I'll always get the identity matrix. So if you think about this right off the bat, A has to be square. So that means it's n by n. So if I'm going to form AB, then if that's n by n, B better be some n by p. Okay? But on the other hand, if I'm going to form B times A, knowing that A is n by n, and B is, say, still n by p, well, these have to be equal. And so that means p has to equal n. So therefore, the inverse of a matrix A is going to be a matrix B with the same dimensions as A. So that's our first takeaway here. And then it becomes clear why it's IN and not just some other I. All right, so that's what a matrix inverse is going to be. But now look here, hopefully I've made you very. I have no idea if you saw that happen, but I just got a FaceTime from my 4-year-old son. I hope it recorded it. Okay, so where was I? I lost my train of thought. All right, so here, can we really say the inverse? So yeah, hopefully I've made you all paranoid now about definite articles. So I say the, meaning there's only one. Right there, you see the. Can we really say the inverse? All right, well, let's find out. So let's say we're given a matrix A, and it happens to be invertible. Okay. So we, up here we talked about the matrix or inverse existing. So that's even a question unto itself. But for now, for the sake of argument, let's say I give you an invertible matrix, and let's say that B and C are inverses of A. Okay? Now we will show B equals C. In other words, the inverse is indeed unique. All right, let's see here. We have B. Well, by the very nature of the identity matrix, B is the identity times the matrix. does nothing to it when we multiply. Well, the identity here, why don't I just be really clever and see that as C times A? Because we know if A is the matrix and C is its inverse, then AC and CA must both be the identity. So I can very well write CA times B. Now remember, matrix multiplication is associative. So that means this is the same thing as C times AB. Well, B is an inverse of A, and therefore AB must be the identity. So that means I have C times the identity. But anything times the identity is itself. So I get C. And lo and behold, I get B equals C, as I promised. All right. Now, in practice, I give you some arbitrary 2x2 matrix, A, B, C, D. I'm telling you here that the inverse of this particular matrix is this mess right here. So what you should notice is I have AD minus BC. How do you remember that? Well, that's like going down that diagonal, A times D, and then subtracting the product on that diagonal. So that's how you remember that. And then how do you remember this? Well, that's nothing more than flipping the diagonal. So A and D, you switch the roles, and then B and C, you simply negate them. Okay? Now, this matrix is going to be invertible, so this one right here has an inverse, if and only if det, which, oops, that's AD minus BC, we don't know what det means, is non-zero. Because if it's 0, this right here is not defined. If that's not defined, then I can't write anything on the right-hand side of this little mapping symbol. So it's kind of interesting that arithmetic, namely AD minus BC, is what actually can be used to give a litmus test for invertibility. Now we know inverses are unique, so this thing I've written here is indeed the inverse if the inverse exists. Let's actually see that it works. So we have ABCD times 1 over AD minus BC times D negative B negative C and A. Now scalars, they can fly out front. So all I need to do really is multiply those two matrices. All right, so that row hits that column. So I have AD minus BC, and then that row hits the second column. So I get negative AB plus BA. Then I take this row and hit that column, and I get CD minus DC, and finally negative BC plus AD. And that, of course, is all times 1 over AD minus BC. So that's 1 over AD minus BC times AD minus BC, 0, 0, AD minus BC. Well, this flies inside and gives us 1, 0, 0, 1. So jackpot. We got the identity. Now the question you'd ask yourself is it sufficient for me to just do A times what I say is A inverse here? Well, no, that is not sufficient, because what's the definition say? The definition says I must compute AB and BA and verify that they're both the identity matrix. So I'm not going to do that here, but I challenge you all to take a little pause and actually perform this times that. And then, of course, don't forget your scalar. All right, so not so surprising here. Say I give you an invertible matrix, and I ask you to solve this particular equation. This has a unique solution for every b. All right, well, think about it. We already know that what? A is unique, this inverse. So if I'm doing AX equals B, I hit it on each side, the left-hand side in particular, with A inverse. So A inverse AX equals A inverse B. Well, A inverse A is what? Well, it's just the identity. So this is X equals A inverse B. Well, looky there. This is saying that the solution, namely X, is exactly this. Since A is unique, nothing else can happen over here. It must be A inverse B for the solution. Now this is really cool because think back to AX equals B when it was like 2x equals 6 from 7th grade. How would you solve this? Well, you did it by dividing by A, canceling, getting x equals b over a. Well, this is nothing more than that, but this happens to be fancier. Because watch. I take a. Now, 1 over a, if you remember your negative exponents, is just a inverse. And I multiply here by a inverse as well. Those give me 1. It's like x equals a inverse times b. Well, a inverse is nothing more than 1 over a, and b times 1 over a is just b over a. So what we've done here is nothing more than what we did in grade school. So the question you should really ask me now is, we know we can solve this equation with the inverse. When do we actually want to end up doing that? Because you're going to find out that if I take a augmented with b and row reduce that, that's equivalent to solving this, right? We've done that ad nauseum. So what is the advantage of actually doing this with the inverse? Well, let me ask you this. Say I ask you to solve ax equals b. 1. I then ask you to solve ax equals some other vector, b2. And ax equals b, and let's say it's some number that's over 9,000. So 9,001. That means you're going to have to solve 9,001 equations, which means you're going to have to row reduce this 9,001 times. No. You don't do that. That's how you go crazy. What's the advantage with this new method? If I compute A inverse just once, how do you compute it? Well, we'll go to that later. But if I compute that just once, then I know my solution is nothing more than A inverse times whatever B I happen to be dealing with right now. So I've reduced the problem to matrix multiplication rather than a series of many 9,001 times that number of row operations. So this is a far more efficient way when you have a system of systems to solve. It's also, of course, of great theoretical importance. All right, if you'll please nerd out with me right now. By GLN of S, that's how you pronounce that, we shall mean those invertible n by n matrices with entries coming from S. So GL here stands for general linear. In fact, it's the general linear group. You don't really need to know what any of these words mean. Just simply know this is a nice shorthand we're going to use. There's a definition that I really didn't show y'all, but let me go and do that now while I'm on this slide. Some people will say invertible. Other people will say non-singular. So if a matrix is invertible, that means it is non-singular. And so if a matrix does not have an inverse, so if A inverse does not exist, we call that a singular matrix. Of course, singular and non-singular sound way more serious. So, if we say those in public, we look much more intelligent. So we'll use those whenever we can, even though invertible is just fine. Anyways, theorem. I have 4 of them here for you. All right, first off, say I give you an invertible matrix. Now you see why I introduced this notation, because it's a whole lot easier to write that than write down, well, anyways. All right, so What this is saying is the inverse of the inverse is just the matrix itself. You all know this already. Negative of negative 2 is what? 2. 1 over 1/2 is 2. And so on, right? The inverse takes you back to yourself. Okay? If I give you two invertible matrices, then their product is invertible. Okay? Not too surprising. Notice that I do not give the converse there. That is a tricky thing. I might give that as a homework problem. It is extremely tricky. Next up, the inverse of a product is just that in reverse. Okay? Pretty straightforward once you actually write it down. And then finally, the inverse of the transpose is the transpose of the inverse. This right here, it's not tricky, but it might be one of the most tedious proofs in linear algebra. I really don't want to do it, to be honest with you. But if you all force me, I will. But all three of these, we'll ignore number 4 for now. All three of these that I have discussed there, I really just don't like you there. Horrible proof. These three we will prove in class. Number 3 here in particular, gigantic star, highlighted with yellow. I'd really like if y'all try to prove that on your own. It's definitely within your capabilities to do that. So please try that. It's a good little exercise. And if you're feeling extremely clever, go ahead and try to prove this abomination right here. All right, now, this comes out of left field, which I like to do. Let's recall these 3 notations. I use them to say swap rows I and j, take row I and multiply it by a scalar alpha. We're assuming alpha is non-zero. And here, I'm taking row I, multiplying it by alpha, adding it to row j, and leaving that in row j. So those are 3 elementary row operations. So now we've recalled that. These actually represent matrices. That is why I've been writing them in this funny fashion all along. I've been training y'all to think of these things as operations and as matrices. So what are the actual matrices? Well, Pij, this is nothing more than the n by n identity matrix with rows I and j swapped. Okay. What's EI of alpha? Well, that's IN with the entry in the II place replaced with alpha. And finally, EIJ alpha, what we got here is I sub n with alpha in the, this is odd, ji position. Okay, so it's a little bizarre. Okay, but you'll get the hang of it. All right, let's see here. Let's say we're dealing with 3 by 3 matrices for the sake of argument. And I'm going to call cap A, B, C, D, E, F, G, H, I. So I'm going to act on A with all 3 of these, one by one. So P13, well, what's that going to be? Well, that's the identity matrix. So it's a 3 by 3 identity matrix with the first and third rows swapped. So that's 0, 0, 1, 0, 1, 0, 1, 0, 0. I swapped rows 1 and 3. So if I do this, let me insert A here, so I'll rewrite this. It's A, B, C, D, E, F, G, H, I. This row hits the first column and grabs the G, then it grabs the H, and then it grabs the I. The second row goes through and only grabs the D, E, and the F. And the last row sweeps through and only grabs the A, B, and the C. Well, lo and behold, what did this turn into? Well, it turned into this matrix where I swapped rows 1 and 3. Not too surprising, given what I told you this is. All right, let's do E, let's say 2 of alpha. And I'll leave it as an alpha so you can actually see it happening. Oh, wait, let me back up a step here. E2 alpha times A. All right, so that's taking the identity matrix and multiplying row 2 by alpha. Okay, and then we have A, B, C, D, E, F, G, H, I. And first row sweeps through and leaves as A, B, C. Alpha sweeps through only the second row. It gives me alpha D, alpha E, and alpha F. And then the last row remains the same. So indeed, I only took row 2 and multiplied it by some constant. All right, let's look at E1, 3, I guess, of alpha times our matrix A. All right, well, remember, what I do to the identity matrix in order to form this is in the reverse 3, 1 entry, so that's right here, I will put an alpha. And otherwise, it's just a plain old identity matrix. Okay, and that's times A, B, C, D, E, F, G, H, I. All right, let's see this happen. First row and second rows sweep through and nothing happens because it's just the identity. Now it's this last one that actually does something. So I'll have alpha times A plus 1 times that G, so that's alpha A plus G. I then hit the second column, I get alpha B plus H, and then finally alpha C plus I. And there we go. That really is alpha times row 1 plus row 3 stored to row 3. That is totally awesome. This was showing you. Let's see, right here. And figure out what the inverse would actually need to do in order to return back to the matrix itself. Slides. And finally, to summarize this, if E is an elementary matrix, so it's one of these 3 entities, and it represents some row operation before in matrix A, then the product EA will have the same result as the row operation. That's what. Now, what's important to note here is this. I do not say AE. I explicitly say EA. So these elementary matrices always work by left multiplication. Because remember, matrix multiplication is not commutative. So it's left multiplication that actually enacts these 3 operations. Now, as a little challenge, what is AE? How can you view those? So that's something for you to ponder. Go back far. All right, theorem. Every elementary matrix is invertible, and the inverse of it is the same as undoing the operation equivalent to E. So in other words, Pij, that swaps rows I and J. Its inverse is Pji. All right. EI of alpha. Well, what's that? That's the same thing. I'm sorry. No, it's not. Its inverse is EI of 1 over alpha. And finally, Eij of alpha, its inverse is Eij of negative alpha. I'll let you all ponder that. Once you figure it out, you'll realize it's pretty obvious. My hint to you is, okay, now why is this all so important? Why do I care that the elementary matrices are invertible and I can write a closed form for their inverses? Well, here's why. So suppose we have some n by n matrix. Then it's invertible if and only if I can row reduce it to the identity matrix. Okay? So let me repeat that. If I can row reduce a matrix to the identity, that means it's invertible. Okay? Now, if EA equals I, or E is a product of elementary matrices, then the inverse has to be the inverse of E. Let's make sense of all of this. Alright, so let's start with this. A is invertible if and only if A reduces to the identity matrix. Alright, so let's say I have some matrix A, and I know that it reduces to the identity. Then I know that I can first form some E1A, and then E2 times E1A, and keep on doing these row operations until finally this last one I do, EK, turns this into the identity matrix. Well, what's that mean? What it means is I have some EK down to some E1 times A equals the identity. What must this then be if I have the identity here? This must be the inverse. And so I get the invertibility of the matrix. The other direction of this, where A is invertible, implies that A row reduces to the identity. I'll drop a hint for you that relates to the very last slide. Row reducing to the identity and being invertible, think of that in terms of solving all of these equations. That's all I'm going to say about that for now. My discussion here, let's see, there we go. It was this. Invertible implies it row reduces. That. Alright. Now, what that last slide does is what it does is it allows us to actually figure out a way to take a matrix, namely A, and determine the inverse of it if it exists. All we do is row reduce. Alright, well, let's try it. I want to determine the inverse of this 4x4 matrix. Well, the process is, if I call this A, I need to form A augmented with the identity matrix. I then row reduce this until I get the identity matrix on the left and A inverse on the right. Okay, so let's do that. So I have 1, 0, 0, 0. I'll pause it here and just write down the business. All right, there we go. Saved you some boredom. All right, what we first observe is this 1 right here. Let me change colors. That pivot is already happy, has zeros beneath it, and it's a 1. So I move on to the next position, namely that one. I need to get zeros below it, check, and above it. Okay, well that means what I need to do here is E21 of -1. All right, next up is to, let me change colors, use this entry to eliminate the 1 above it. So that means I'm going to do E32 of -1. All right, the next one is using this entry to eliminate the 1 above it. Oh, I wrote a 2 here. I meant 2, oh, what did I mean? I meant E32. All right, I want E43 of -1. All right, and that's the end result. So I have 1s, oh, well, first off, I got the identity here. I think we all see that. I got I sub 4. That means right here, this must actually be the inverse. So I notice is I have 1s on diagonal and -1s on the super diagonal. Now, why is that of interest to me? Because look, what is that matrix? If I were to write that down, it would be in the 1, 2 entry, you put a -1. So let's see here. In the 1, 2 entry, I put a -1. What would this be? In the 2, 3 entry, I'd put a -1. And in the 3, 4 entry, I'd put a -1. So somehow encoded in A inverse here, you'll see these 3 operations. That's really interesting. It won't always be this way. The reason it worked out this way, well, we'll discover as the course goes on, but there's some kind of intermingling that didn't happen that normally happens when you do these row operations. All right, and then the last thing I want to just kind of mention here, one last thing to ponder, is what I said earlier about that converse, or the conditional, I don't remember which direction it was. So the process of doing this, find the actual inverse via row operations, is equivalent to simultaneously solving AX equals EI for 1 through N. So use that. First off, figure out why that is true, and then use that to actually answer, you should apply all this. So ponder that, please.